Hello everyone, welcome to Stats with Supreetha. In the last episode, we learned about variance and standard deviation. Today, we are going to answer a very important question. Why do we divide by n minus 1 instead of n when calculating sample variance? It looks like a tiny change, but this tiny change is one of the smartest fix in statistics. This is called Bessel's correction. Bessel's correction is named after a German astronomer. He worked with stars and planetary measurements. But here's the interesting part. The problem he helped to solve was much bigger than astronomy. It was about estimating things correctly. Imagine you want to know how spread out the marks of all students in schools are. Can you measure every student? Probably not. So you take a sample, and that sample help you estimate the whole population. But there's a catch. The estimate can be biased, and Bezos found a way to fix it. That's why this correction became so important. Our goal is simple. We want to use small sample to understand a large population. For example, suppose there are 10,000 mangoes in a farm. You cannot check all of them. So you pick 20. Now you want to know how much their weights vary. That's sample variance. But here's the problem. If you use normal variance formula directly, it usually gives smaller answer than reality. That means it underestimates the spread. Why? That's the mystery. And the clue is hidden in sample mean. What is Bessel's correction? Now, Bessel's correction is very simple. It uh, normally variance looks like this: sample sum of squared difference divided by n. But with Bessel's correction, we divide by n minus 1. That's it. Just change in one number. But why? Because dividing by n makes the variance biased. It makes the spread look smaller. By dividing n minus 1, it stretches a little and corrects the bias. Think of it like this. If your shirt shrinks after wash, you stretch it back. Bessel's correction does the same thing for variance. So the culprit is estimating the mean. This is the main reason. Usually we do not know the population mean. So we calculate the sample mean. Let's say your sample is 246. The sample mean is 4. Now we measure the distance from 4. 2 is 2 away. 4 is 0 away. 6 is 2 away. Looks neat. But notice something. That mean comes from the same data and especially positioned to sit in the center. It naturally pulls all points to closer, so that makes the spread look tighter, like a magnet. That's why sample variance becomes too small. So why bias happens? Bias means your method keeps making some mistake, same mistake. Okay, here mistake is underestimating variance. Why? Because the sample mean is the best fit for that sample. It minimizes the distance. That sounds good, but it creates an illusion. Imagine three student, uh, students standing and choosing their center point. Of course, the every center make everyone look closer together. That's exactly what happens in statistics. So dividing by n ignores the shrinking effect, and that create bias. Now comes the famous idea, degrees of freedom. Don't worry, it sounds scary, but it is easy. Suppose you have 5 numbers, that means 5 pieces of freedom. But once you calculate the mean, one rule appears. All divisions from that mean must add up to 0. That means if 4 values are known, the last one is forced. It cannot move freely. So, 5 total values minus 1 restriction equal to 4 free values. That That's why we divide by n minus 1, because only n minus 1 is truly free. This is the heart of Bessel's correction. Let us make this real. Okay, suppose we measure heights of 5 students and we calculate variance. Using n, variance is 18 centimeters square. Using n minus 1, variance is 22 centimeters square. And let's say the actual school variance is 23 centimeters square. Which one is closer? 22. That's why Bessel's correction works better. A sample sees only a part of reality, so we slightly adjust it. It's like zooming out for a clear picture. So, is it always perfect? Very important point. Bessel's correction removes bias, but that does not mean it's always absolute best. Sometimes statisticians look at something called mean square error, or MSE, that measures total error. In some cases, another denominator may give lower mean square error. But for unbiased variance estimation, n minus 1 is the gold standard. Also, for standard deviation itself, the correction is not fully perfect. It mainly fixes variance. Still, it is the best practical choice. So, when to use Bessel's correction? Use Bessel's correction only whenever you are working with sample and you don't know the population, which is almost always. That means in research, in machine learning, in survey, in business reports, in experiments, even in softwares like in Python, R. That means Bessel's correction is active. Okay. Now, so let's recap. The problem: dividing by n underestimates spread. The reason: the sample mean pulls values closer. So the fix is dividing by n minus 1. The idea: 1 degree of freedom is lost. So the result: a more honest estimate of population values. That's Bessel's correction. A tiny change but a huge impact. And that's how statistics stays truthful. If you found this video helpful, don't forget to like, share, and subscribe to Stats with Supreetha. Thank you so much.